Alrighty, hello and welcome. Whoa, sounds a little. Hello and welcome to our third class, second lecture. First class was just intro to the course. Where we left off last Thursday, we were talking about the rules for significant figures, and that is a discussion that we will be continuing today. Except now we're going to be discussing the rules for significant figures with respect to multiplication and division. All right, so we've learned, just a quick recap, we've learned how to determine the number of significant figures in a number. We've learned how to apply the rules for adding and subtracting, taking into account the precision of each number and how that affects your answer. And now we are going to look at the rules for using significant figures as we add and subtract measured quantities. All right, so first, let's start with the rule. So when you multiply or divide two numbers, your answer must have the same number of sig figs as the number you multiplied or divided with the least. So your answer must have the same number of significant figures as the number with the least. All right, so that is how you apply the rules for significant figures when you are multiplying or dividing. So let's do a few examples. Okay, so let's start by let's do 11 times 3. All right, now when you punch in this into your calculator or do it in your head, we all know what 11 times 3 is, right? 11 times 3 is 33. But as we mentioned last week in lecture, that the correct answer, every correct answer in this class has 3 components. There's the value, the units, and the sig figs. Now 33 is the correct value, but we need to determine how many significant figures should this answer have. And when you look at this number, 11 has 2 significant figures. 3 only has 1 significant figure, so our answer can only have 1 sig fig. So you count off 1 sig fig. The rest we have to round. Now 3 rounds down, so our answer after rounding will be 30, because 30 only has 1 sig fig. Excuse me. Now, this part, I remember when I first learned this as a student, this part, sorry, I just said this, fart. This part feels straight up wrong, because you're like, math is math, and 11 times 3 is 33, not 30. To which I reply, remember, we talked about where sig figs come from. Sig figs are a result of measurements, right? They're that last imprecise digit, that last imprecise decimal place. And so we have to incorporate them in our mathematical operations to reflect the precision of the instruments that took the measurements. So, in other words, if you want 11 times 3 to be 33, yes, so the answer, no. Okay, Rox, great question. You don't put both answers. The answer is just 30. The answer is just 30. I wrote 33 first to kind of show you the process, but you get your value, look at the value, apply the rules for sig figs, and the answer, the final answer, is just 30. 33, if you put 33 down as your answer, that would be incorrect because it is the wrong number of sig figs. If you want 11 times 3 to be 33, you need to multiply 11 times 3.0. All right, if we look at our sig figs here, 11 has two significant figures, 3.0 has two significant figures. So when you multiply these two together, the answer is 33, and 33 has two significant figures, so we do not need to round at all. Yes, Rox, you are not alone. Whoa, hang on. Something just happened to my live stream. There we go. There we go. Rox, you are not alone. This is probably the most challenging thing, especially early on in this course, for the majority of students that I teach. The only way to get used to this is doing problem after problem after problem. And I have to tell you, you gotta do enough of these so that they feel like second nature. Yeah, you're totally not alone, but you gotta get the repetition in because this is the one thing in this class that never goes away. All right, we're doing it day 1, day 2. We'll be doing it till the day we die out of this course. The last day of class, on the final exam, you will need to be proficient at sig figs to do well. So it's challenging, it's difficult, but now you know what to zero in, you know what to practice, because this is an important thing. Okay, all right, let's do maybe a couple more examples here. How about, oh, yes, Brianna, that is exactly correct. Totally, yeah. Okay, let's do another example. Let's do, sorry. Here we go. Let's do 25 times 4.0. Yes. So the thing is, and this is important to note, calculators don't understand how to do sig figs. So calculators do not understand sig figs. So if you punch it into your calculator, 3 times 11, it'll tell you the answer is 33. You have to apply the rules for sig figs after, once you see that answer, you got to take that answer and then you have to apply the rules for sig figs. So if you're using a calculator, you still got to keep them in mind. Yeah, Daisy, you totally can. Yes, absolutely. All right. So let's go ahead and do this problem. 25 times 4.0. All right. Now, when you do this multiplication, you punch it into your calculator. Your calculator will give you the correct value for your answer, which is 100. Now we have to ask, how many significant digits should this number have? Daisy, you are so welcome. Now, 25 has 2 sig figs. 4.0 also has 2, but you'll notice 100 only has 1. So the question here is, how do you write 100 with 2 sig figs? All right, because 100 only has 1 sig fig, we need to write it with 2. And the answer, there's only one way to do this. You have to use scientific notation. All right, you have to use scientific notation to write 100 with 2 sig figs. Carolina, the answer is not 99 because that's 1 lower. We have to write the exact value for 100, but with 2 sig figs. And scientific notation is the way to go. Yep, Robert, exactly. So scientific notation, and we'll do a couple examples with scientific notation just so we all get the swing of things. In scientific notation, you take your number and you take the decimal for that number and you place the decimal behind the first non-zero digit. So we need to roll this decimal 2 spaces over. So the number 100 in scientific notation is 1 with that decimal right behind it. But the thing is, 1 has a different value than 100. To make sure this has the same value, we're going to multiply this number 1 by 10 to the power of 2. If you punch into your calculator 1 times 10 squared, the answer is 100. These two have the same value. But the beauty of scientific notation is we don't have to write this as 1 times 10 to the 0, times 10 squared. We can write it as 1.0. And 1.0 has 2 sig figs. So scientific notation allows you to write a number with the same value as 100, but that only has 2 significant digits in the answer. So our answer here is 1.0 times 10 squared. That is how you write 100 with 2 sig figs. Rux, great question. Technically, you can do it any time. It's never wrong to do scientific notation. But the only time when you have to do scientific notation is when you have an answer that needs a specific amount of sig figs that number can't accommodate through writing or adding decimals. See, because the problem here is normally when we need to write something with more sig figs, we just add a decimal, right? But the problem with 100 is if you write 100.0, that doesn't have 2 significant figures. That has 4 because our non-zero digit is significant, our 0 to the right of the decimal and at the end of the number is significant, and then these two zeros are significant because they're in between. This has 4 sig figs. Usually when we need to add sig figs, we just add 0.0, right? But 100.0 has 4 sig figs. 100 has 1 sig fig. And the number of significant figures that we need is in between. Right, we need to write a value for 100 that has 2 sig figs. And so when you're in between those kind of two extremes of the number of sig figs your number has versus the number of sig figs that you get when you just add 0.0, when you're in between there, that is when scientific notation comes into play. That's how you know you need to use it. All right, so just a quick brief reminder on how to write with scientific notation. Just so we're all on the same page. Let's talk about it here for just a minute. So, as I said earlier, when you write a number in scientific notation, you take the decimal and you move it so that it's behind the first non-zero digit. So to write 4,132 in scientific notation, we'd write 4.132. Now for this equal sign to be valid, 4,132 does not equal 4.132. So we need to multiply it by 10 to the third. And the place that you get that third from, that power, is we jumped over 1, 2, 3 spaces. That's how you know it's 10 to the third. When you're writing in scientific notation, you need to make sure, so the sig figs in your number, only the 10 to the third doesn't add any. So the only sig figs come from this number right here, 4.132, and you have to make sure that the number of sig figs you start with equal the number of sig figs you end with. So for example, if I had you asked you to write 6,010 in scientific notation, again, you find that decimal place and you bounce it over 1, 2, oops, got a little ahead of myself, 1, 2, 3 spots. So 6,010 in scientific notation would be 6.01. This would be times 10 to the third. And again, it's 10 to the third because we had to bounce that decimal over 3 places. You'll notice that I lost or I'm missing a 0. That's because it wasn't significant. In our original number, there's only 3 sig figs. So in scientific notation, we only have 3 sig figs. They always reflect each other. You never gain any, you never lose any. Something that you'll also run into, you should be aware of, if I asked you to write 0.00340 in scientific notation, you find that decimal, just right here, and we're going to roll it back 1, no, I can do better. There we go, 1, 2, 3 spots. Now you'll notice here that we are moving it in the opposite direction. So this will be 3.40. Again, we have to keep 3 sig figs. But you'll notice here that we moved the decimal in the opposite direction, right? We moved it to the right. So this would be 3.40 times 10 to the negative third. All right. Because 0.00340 doesn't equal 3.4, it equals 3.40 times 10 to the negative third. So when you move the decimal place to the left, you'll get a positive exponent. When you move it to the right, you get a negative exponent when you're writing in scientific notation. All right. So that's scientific notation. Those are the rules for multiplication and division. I want to do a few examples before we leave sig figs, where we're mixing operations, where we're multiplying and dividing. No, sorry, we did that. When we're multiplying and adding, or dividing and subtracting. Alma, great question. Alma, whenever you're writing in scientific notation, you always move the decimal so that it's directly to the right of the first non-zero digit in the number, wherever that lands. Yeah, Robert, spot on. Okay, let's do some mixed examples. So let's look at sig figs with addition, subtraction, multiplication, and division. Everything in the mix. Oops. Yep, Daisy, that is correct. That is correct. Okay. So let's do some mixed examples. Let's do. So how would you, for example, tackle a situation like this? All right. How would you tackle a situation like this? This one's tricky because you have both addition and division, which have different rules for sig figs. So how do you handle it? And the answer is you follow the algebraic rules for operations. You follow the normal order of operations. So first, if you were to just solve this, you would start by doing the addition in the numerator. You'd solve that first. Then you take that value for the numerator and then do the division. That's exactly what we're going to do here, and we're going to apply the rules for sig figs as we go. So taking that numerator, we have 2.7 plus 9.8. All right, so let's add these together. 2.7 plus 9.8. The value for my numerator is 12.5. All right, over 4.100. All right, now we just did addition, right? So that's a different rule than what we've been using so far today because we've been doing multiplication, division. But for addition, you just look at the last decimal place. 2.7 has its last significant digit in the tenths place, the first decimal place. 9.8 has its last significant digit in the first decimal place. So our answer, the answer to this sum must have its first decimal place, must have its last significant digit in the first decimal place, and it does. 12.5 has a sig fig in that first decimal place, which means we do not need to round, we don't need to add any zeros, we're good. The sig figs for our numerator are good. Now, we take our numerator, 12.5, and divide it by 4.100. Now, the value that I'm getting is very, very long. It's 3.04878049. All right, that's the correct value. What about the correct sig figs? Well, we're doing division now. Division has different rules than multiplication. Division has different rules than addition and subtraction. In our numerator, we have 3 sig figs. In our denominator, we have 1, 2, 3, 4. When you're dividing, you have to roll with the fewer number of sig figs, which is our numerator, so we will be limited to 3. You count off your first 3 sig figs and then ask yourself, does 8 round up or down? And the answer is it rounds up. So our answer, correct value with the correct sig figs, will be 3.05. All right, 3.05. Let's do one more example. All right, let's do let's do 112. Rox, there's totally hope for you. If you're willing to practice, there is absolutely hope. Let's do 112 minus 97 times 3.6. Again, we got to take this one step at a time and follow algebraic orders of operations. So we're going to do inside our parentheses first. 112 minus 97.0. Now, my calculator is telling me that the answer is 15. Let's look at our sig figs. We just did subtraction. The last significant digit in 112 is in the ones place. The last significant digit in 97.0 is in the tenths place. Because 112 is least precise, our answer must have its last sig fig in the ones place, and 15 does. So we don't need to add a 0.0, we don't need to change it. It's good the way it is. Now we have to do our multiplication. 15 times 3.60. My calculator is telling me that my answer is 54. Oops. So I want that in black. The question is, what are the sig figs? Is that the correct number of sig figs? Let's look. We're doing multiplication here. 15 has 2 significant digits. 3.60 has 3. Our answer must have the same as the number with the fewest, right, when we're doing multiplication? So our answer needs 2 sig figs, and guess what? 54 has 2 sig figs. So that is correct. That is the correct value with the correct sig figs. Every once in a while you do a problem where the answer that the calculator gives you has the right number of sig figs. And that is the case here. So every once in a while you get lucky, but you always got to ask the question. You always have to be actively checking to see if it's correct or if it's not. All right. We have just a few topics left in chapter 1. I believe we're still in chapter 1. Yes, we're totally in chapter 1. let's talk a little bit about unit conversions. All right, now we've talked a little bit about units before, right? I showed you the metric prefixes, and I was like, these are worth memorizing, or at the very least having on your equation sheets that you're going to make for your exam to save you time and prepare you. So we've already talked about unit conversions a little bit, but we need to talk about unit conversions within the context of significant figures. Now, there are two basic systems of measurement that that we run into. In science, we use the metric system predominantly, but things are still measured in English units, especially because we live here in America, who persists in the use of English units as opposed to the metric system, like the rest of the world. And so, so we have to know how to handle both, basically. Now, whenever you are converting from metric unit to metric unit, so there's two fundamental types of conversions that you'll do in this course. There's whenever you convert metric to metric, or if you're converting between English units, English to English. All right, these, whenever you're doing a unit conversion within a system, this is exact. We say it's exact. The reason why we call these conversions exact is because they're not measured, they're defined. 1 foot is defined as 12 inches. It's not measured, it's the definition of a foot is it has 12 inches. 1 meter is defined as having 100 centimeters. Again, you don't have to measure them, it's by definition. And because it's not measured, these conversions have unlimited precision. They have infinite sig figs, all right? A way to think of an exact conversion is it's like it has infinite sig figs. All right? They'll never limit the significant figures of your answer. The sig figs of your answer will be determined by whatever initial starting measurement you had. But the unit conversions themselves are exact. They'll never limit you. Now, if you convert from the metric system to the English system, or if you convert from the English system to the metric system, because they're different units of measure, the conversions are not based on definitions, they're actually measured out. These unit conversions are measured. And that means that they have the potential, they can limit the sig figs in your answer. They don't necessarily, but they can. All right, and that's key. Sometimes they will, sometimes they won't, but you have to be aware that these unit conversions do come with significant digits because they're measured and they have the capacity. They can limit your answers. Let's do a few examples to kind of illustrate what I mean. Let's convert 14, well here. So let's do some examples. Let's convert 14.7 feet to inches. All right. Now, the way you do a unit conversion is you have to set up your ratio. All right. You have 14.7 feet. If we want to convert from feet to inches, that means that we want feet to cancel. So we're going to put feet in the denominator. We want to be left with inches, so that goes into the numerator, all right? Now, I haven't even thought about how many inches are in a foot yet. First, I'm just setting up my ratio. But once I have, now I think, okay, how many inches are in a foot? And the answer is there are 12 inches in 1 foot. And now I'm all set up to crunch my numbers. Feet cancel feet. The only unit left standing is inches, which is good because I was asked to convert from 14.7 feet to inches. So I go 14.7 times 12, because it's in the numerator, is, now the value that I'm getting is 176.4. The question is, how many sig figs should my answer have? And to answer that question, you have to look at the number of sig figs in your original measurement. 14.7 has 3 sig figs. It doesn't matter. I don't look at my unit conversion because inches and feet are part of the same system of measurement. They weren't measured. It's defined that 12 inches are equal to 1 foot. So those two numbers in the unit conversion don't have sig figs because they're part of the English system. Rox, if you struggle with the setup, don't think about the numbers. Focus on canceling. Focus on canceling units, and then once you've set up the units to cancel, then you add the numbers. 12 inches and 1 foot. But first, you'll notice I put in the units so that they'd cancel, and then I figured out where the numbers went. Daisy, exactly. Our final answer will have 3 sig figs, so we have to count off 1, 2, 3. 4 is going to round down. So my final answer, yes, Carolina, because it's English to English. Because they're both in the English system, it doesn't limit us. My final answer is 176. That's the correct value with the correct sig figs. And now I need the units to put the cherry on top of this sundae. 176 inches, totally. Now let's do a couple more. Let's do an example where we want to convert. How about we convert 42.0 meters to kilometers? Daisy, great question. Daisy, we got to roll 176 because our answer needs 3 sig figs, and 176.0 has 4. All right, let's do 42 meters to kilometers. So 42.0 meters, we need to convert to kilometers. Totally. Now, again, I'm not even going to think about numbers. I am just going to plug in my units. I want, Daisy, my pleasure. I want meters to cancel, so I'm going to put meters in my denominator. I want to be left with kilometers, so that goes up in the numerator. Now, kilometers. Kilo means 10 to the third. That's what that prefix means in the metric system. So 1 kilometer is 10 to the third meters. All right. Meters cancel meters, leaving us with kilometers, which is good. And now we have to punch into our calculators 42.0 divided by 10 to the third. And my calculator is telling me that my answer is, oops, no, it's not telling me that. It's telling me my answer is 0.042. The question is, does this have the right number of sig figs? And let's take a look. Because kilometers and meters are both part of the metric system, again, it's a conversion within the same system. This unit conversion will not limit my sig figs, all right? I just have to pay attention to the sig figs in my original number, and 42.0 has 3. When I look at my answer, 0.042 only has 2 sig figs, so I need to add a 0 to the end. That way, I have 3 significant digits in my answer, and I need to add my units, kilometers, if my answer is going to be complete. So 42.0 meters converted to kilometers is 0.0420 kilometers. Ariana, great question. The reason why it's 10 to the third is because that's the definition of kilo, which is that K in the metric system. Anytime you have kilo anything, kilometers is 10 to the third meters. Kiloliters is 10 to the third liters. Kilograms is 10 to the third grams. Because kilo is 10 to the third, and 10 to the third is 1,000. So that's where that comes from. All right, let's do one more unit conversion. This time, let's convert from 55 centimeters to inches. Now, you may not know this unit conversion off the top of your head. 1 inch is 2.54 centimeters. Now, in this case, yeah, exactly. In this case, 1 inch is 2.54 centimeters. In this case, because inches is English and centimeters is metric, this unit conversion is not exact. This unit conversion has 3 sig figs in it. So it has the potential to limit our answer. Now let's go ahead and calculate this. Yeah, Ariana, you are so welcome. So 55 centimeters. If we want to convert this to inches, we need to put centimeters in our denominator and inches in our numerator so that centimeters cancel, we're left with inches. Once we have our units in place, now we add our numbers. 1 inch is 2.54 centimeters. When you multiply these together, Daisy's spot on, comes out to be 139.7. But now you have to ask, how many sig figs can my answer have? Centimeters cancel, which is good. But how many sig figs am I limited to? My unit conversion has 3 sig figs. My initial measurement has 2. So in this case, I'm limited to 2. My unit conversion doesn't affect it in this case. We'll do another one in just a moment. But let's finish this problem. 9 is going to round up. So our correct value with the correct sig figs will be 1.40. So 140 inches, because again, this has 2 sig figs, and our answer is limited. Limited to 2. All right. Let's do another example. One last one. Okay. Let's convert 4,205 inches to centimeters. All right, now, first things first. You always focus on setting up your units to cancel before you even think about your numbers. We want inches in the denominator, so they cancel with inches. We want centimeters in the numerator. And now, once we've placed them, we know that 1 inch is 2.54 centimeters. So we can punch this in, 4,205 times 2.54 is 10,680.7. When you look at your units, inches cancel inches, we're left with centimeters, which is fabulous. Now we have to ask, how many sig figs can we have? Well, our initial measurement has 1, 2, 3, 4 sig figs in it, but our unit conversion only has 1, 2, 3. So in this calculation, our unit conversion is going to limit our sig figs. We can only have 1, 2, 3 sig figs. 8 is going to round up. So our final answer will be 10,700 centimeters, because this number only has 1, 2, 3 sig figs in it. All right. So that's how you handle significant digits and unit conversions. If it's within a system, so if it's metric to metric, English to English, doesn't limit your sig figs. If it's metric to English or English to metric, if you're crossing systems, then your unit conversions, significant figures matter. All right, so that's just something to keep in mind. You run into it every once in a while. All right, now the last concept, the last topic within this chapter is something called density. Density. Now, density is a ratio of the mass of an object or a substance to its volume. It's a ratio of a mass to volume. Sorry, Aaron, I'm just now seeing your comments. Oops. So density is a ratio of mass to volume, all right? And the equation for density, which I would totally recommend adding this to your exam equation sheet, density is equal to the mass of a substance divided by its volume. All right, so the units the density will usually have is it'll have a mass unit, some mass unit over some volume unit. So Marcelo, I see your question, but I'll circle back and answer that at the end of lecture. Um, so it's going to be density will have units of some mass unit over some volume unit. So the units that you run into for density vary wildly because they could be any mass unit over any volume unit. Typically, you'll see grams per milliliter is fairly common. You can also see, it's not uncommon to run into grams per liter, but it could be kilograms per liter. It could be really anything, any mass unit over any volume unit. And density kind of gives us our first foray, I said foyer, but that's a different thing, foray into problem solving in a chemical context because it relates two different things, mass and volume, two different measurements together in a ratio. So this equation for density allows us to solve problems like the following. So consider the following example. Let's see, water has a density of 1.008 grams per milliliter. What is the mass of 50.0 milliliters of water? All right. Now, in this class, you want to be very focused on problem solving, right? Because at the end of the day, when you think about it, watching lecture is useful. Reading the book is useful. But in the exam context, am I going to test you on your ability to read a textbook? Nah. Am I going to test you on your ability to watch me lecture? No. I'm going to test you on your ability to solve problems. So that should be the primary focus of your study time in this class, should be solving problems. And every time you solve a problem, you sit down to solve a problem in this class, you should always start with identifying what you're trying to find. Sorry, I need to open this in a new slide. Here we go. You always begin with identifying what you are trying to find. All right? And in this problem, you can see it here. It's what is the mass of water. So we want to know what is our mass. We want to know how many grams of water are in the sample. Once you've identified what you're trying to find, next you want to identify what you are given in this problem. Every problem gives you different things. You want to identify what you're given. One thing that jumps out at me, you'll notice that we're given a volume, right? We're told that the volume of water that we have here is 50.0 milliliters, right? The second thing we're given is the density. We're told what the density of water is. We're told that the density of water is 1.008 grams per milliliter. Now, you may look at this problem and think that's all there is. That's all we're given. But we actually have one more piece of information here. Right? We have one more piece of information, and it's hidden inside this quantity. It's hidden inside density. Anytime you're given a value for a quantity that has an algebraic equation, you should write that algebraic equation out as part of your given information. And density has an equation. Hopefully you've already added it, or after this lecture, you will add it to your equation sheet. There's an equation for density, and that becomes part of our given information. Density is equal to mass over volume. Now check this out. If you look at this equation, we've been given density, and we've also been given volume. So what does this algebraic expression allow us to find? It lets us find mass, the mass of water, and look at that. That's what we're being asked for. When you write out the algebraic expression for a given quantity, that equation often becomes the roadmap you follow to solving the rest of the problem. So write it out every time. It will pay dividends in gold. All right. So now that we've identified the roadmap, let's actually do some algebra and solve this problem. Oops. All right. So we identified that we could find the density of water we know the density of water. We can find the mass of water using the equation for density. We got to do a little bit of algebra here. We're going to start by multiplying both sides of this expression by volume so that it cancels and we isolate mass on one side of this equation. So mass is equal to the volume of water times the density of water. Now we know both of these quantities. Now that we've isolated mass, we can plug them into this expression. Our volume is 50.0 milliliters, and our density is 1.008 grams per milliliter. You'll notice when you multiply these together, milliliters cancel with milliliters, which is as it should be, because we're solving for mass, so we should cancel our volume units and be left with a mass unit, and grams is a mass unit. All right, now we're ready to crunch our numbers. 50 times 1.008. The value that my calculator is giving me is 50.4. That is the correct value. We need to ask, does it have the correct number of sig figs? Well, our first number, our number for our volume, 50.0, has 1, 2, 3 significant digits. Our value for our density has 1, 2, 3, 4. And we know that our answer must have the same number as the one that we multiplied with the fewest sig figs, right? So our answer has to have 3 sig figs. And you'll notice that 50.4 has 3 significant digits, so its sig figs are fine. The only thing missing from this answer being complete is we need to add our unit. So the mass of 50 milliliters of water is 50.4 grams. All right, that is the mass of water. Let's do another example. All right, let's do another example. Determine the volume occupied, oops, by 18.9 grams of water in liters if if the density of water is 1.008 grams per milliliter. Ariana, let's unpack this algebraically and figure it out one step at a time. Kind of like my my philosophy, my approach with unit conversions. I don't try to think ahead of time. Do I need to multiply both sides by volume? I'm just gonna take it one step at a time and then do the algebra that's required. So we might. I'm not sure off the top of my head, but we'll live in the moment and cross that bridge when we come to it. All right. So let's start unpacking this problem. The first thing you do when you work any problem in this class is you want to identify what you're trying to find. All right. And in this case, we are trying to find the volume of H2O in liters. All right. So not just in any unit, but in liters. Let's look at what we're given. We're given our mass of water. We're told that our mass is 18.9 grams. We're also given the density of water, 1.008 grams per milliliter. All right. And just like last time, whenever you're given a quantity that corresponds to an equation, write that equation out. It will be useful. The density of water is equal to its mass over its volume. And one thing you'll notice is we've been given density, we've been given mass, so this equation will allow us to find the volume, and the volume is what we're after in the first place. So we have some algebra to do. Ariana, we're about to see if we do need to multiply both sides by V. But now that we know where algebra is heading, let's unpack this. Density is equal to mass over volume. And so yeah, turns out we do need to multiply both sides by volume because volume is in the denominator of our expression and we need to isolate it on one side of the equation. And to do that, we need to jailbreak it out of our denominator. So multiplying both sides by volume gives us this new expression, volume times density is equal to mass. The thing is, we still need to isolate volume. It needs to be by itself on one side. So we're going to divide both sides by density, and we get a new expression, volume is equal to density divided by mass. Now, we're given our density, it's 1.008 grams. Oh wait, hang on. My bad. If I just look at what I've written above, volume is equal to mass over density. There we go. So density goes in our denominator, 1.008 grams per milliliter. And then mass, 18.9, all right. The mass of water is 18.9 grams. One thing you'll notice is our mass units cancel, which is awesome. 18.9 divided by 1.008 comes out to be 18.75. Now we need to look at sig figs. Our numerator has 3 sig figs. Our denominator has 1, 2, 3, 4. So we can only have 3 sig figs in our answer. 5 rounds up. So our volume is 18.8 exactly. Now what units? You have to be careful here. You have to be careful because when you look back at the original problem, I asked for the volume in liters. But when you look at where we are mathematically, what volume unit do we have here? We have milliliters. So this is 18.8 milliliters. Often students will just get a value and go, oh, liters are the correct unit. Slap liters on this thing. That'll get you the wrong answer. That'll get you the wrong answer because we're not dealing, we haven't found our unit, our volume in liters yet. The units we're dealing with are milliliters. So we need to do a unit conversion to convert 18.8 milliliters to liters. So we have one last step in this problem. We need to set up our unit conversion to cancel milliliters, so that goes in the denominator. We want to be left with liters, so we put liters in the numerator. And now, yep, Daisy, exactly. 1 liter is 1,000 milliliters. Another way to put that is 1 milliliter is 10 to the negative third liters. They're both exactly the same. You can use either one. It'll come out okay. What is important is that milliliters cancel. They do. And when you multiply 18.8 times 10 to the negative third, the value that my calculator is giving me is 0.0188. Correct units are liters. And now if you look at our sig figs, 18.8 has 3 sig figs. 0.0188 also has 3 sig figs. So this is our final answer. That is our volume in liters. The volume that 18.9 grams occupy. All right. Okay. That wraps up chapter 1. And I'm looking at where chapter 2 starts, and this just seems like a clean break where we're going to end. So we're going to go ahead and stop lecture here. We'll resume on Thursday with chapter 2. We'll dive right into chapter 2. But I don't feel like, I feel like this is a good place to stop. It caps off the discussion of unit conversion, sig figs, density. We'll pick up on Thursday talking about atomic structure. All right, Marcelo, I have not forgotten about your question. Let me see. There's a module for significant figures blank document worksheet that we can print out. It says to bring it to lab. Oh, okay. So oops, hang on 1 second. That's the way it looks. So this is in the spirit of full disclosure, this is my first time teaching this class at this college, and so I've taught all this content before, but really where things differ college to college is in the lab curriculum and how they set up and execute the lab. So one of the things that Southwestern College does, the whole chemistry department does this, and so I'm just following suit, is the lab assignments aren't available to, or at least what I've been told is that they're not available to do or turn in until the lab period that you're registered in, and it is true that you cannot submit your lab assignment until the time window of your lab class. And some of the pre-lab assignments will be kind of like quizzes, similar to the pre-lab quiz. And so those quizzes, for example, you won't get access to those until your lab starts. But I was just like 15 minutes before lecture, I was looking at what our lab situation was tonight. And the in-lab assignment is a worksheet that you can like print up, fill out, scan, and upload. And so you won't be able to upload it. You won't be able to turn it in until your lab period starts, and you have to do it before the lab period ends. But Canvas does make it available to you before the lab starts. So this is one instance where you can begin it early. Let's see. Besides the lectures, textbook, homework, well, where density word problems. Ariana, great question. Whoops. There we go. This is the best tip that I have, and this works for any subject in chemistry. Google the name of your class, Chem 100, whatever the subject is. In this case, it's density. Chem 100 density worksheet PDF, and Google will literally spill out endless numbers of worksheets, example problems for you to do, in addition to like the practice homework that's been assigned. It's just unlimited, and they're all from like universities. I don't know why this is, but like University of Wisconsin is like really good, always near the top of the Google searches as far whenever I Google a worksheet. So that will give you like an unlimited number of practice problems, and I highly recommend doing as many problems as you can get your hands on. Whoops, hang on. Rock's question: are you on a Mac or a PC? Okay, cool. So if you're on a Mac, I believe um, So I believe that you can. I believe that you can use rocks preview to write on a PDF, like with a like you can use a little pen tool, um, or you can add text to it, even if it doesn't have fillable format, even if it's not created with fillable um, formats. So you still need to do it on the actual worksheet, but you'll just have to manipulate it directly in the PDF and then save and upload it. Ah, Juliana, Discord link invite invalid or expired. Ah, okay. Juliana, I'm sorry. I thought I posted a link that would be available forever. Um, but I probably messed that up. Yeah. Alonda, straight up. Or you could use pages to write on it / in it as well. Let me need to open Discord. Let's see. Yeah. No worries. Oh wait, where is it? Oh, way over here. Let's see. Let's edit this. New link. All right. Copy. Okay. Boop. And yeah. Totally. All right, just dropped it on Canvas. Okay, so I'm gonna go ahead and close down our stream here. We'll be resuming um, in lab in about 15 minutes, but this gives us the time to walk away from our screens, give our ears a chance to breathe, eat something, and awesome, and welcome to Discord. I'll see you all there shortly. Later, dudes.